Okay, for our homework hanging signs worksheet, we've got hanging signs, and we know hanging signs have constant velocities of 0. Constant velocity means balanced forces. We're simply going to take these forces that are at angles, and we're going to balance them. All the forces to the left equal all the forces to the right. All the forces up will equal in magnitude to all the forces down. So our T1 will be broken into a T1 cosine 60 for the leftward force. It's cosine because it's adjacent to the angle. And then T1 sine theta, or sine 60, going up because it's on the opposite side. T1 is pulling to the left and to the up. T2 is pulling to the right and pulling up. So that rightward pull would be T2 cosine 35, and that upward pull would be T2 sine 35. The mass is 10 kilograms, so the mass times gravity, mg, force of gravity, would be 100. Mass times 10, sine's near Earth. For our free body diagram, this time I decided I would just show the forces, the leftward forces, the rightward forces, the upward forces, the downward forces, so that way my net force equations become very easy. So since the free body diagram's a box, I felt like it gave me the freedom to put in it whatever I wanted that made most sense to me. In this case, this is what I decided to do. If this was a dot and it was a test, then we would have mg down, T1 going up to the left, T2 going up to the right. So I've got my leftward force T1 cosine 60 is equal to my T2 cosine 35. Left is equal to right. That's my summation of forces in the x direction. For the summation of forces in the y direction, I have T1 sine 60 plus T2 sine 35, the two upward forces, and they're balanced to or equal to the downward force of mg. Let's start with the first one, T1 cosine 60. I can put cosine of 60 into my calculator. I get 0.5. I can also put cosine of 35 in my calculator, and I get 0.819. I'm choosing 3 decimal places. We say 2 in class, but I'm choosing 3 because a lot of people are used to doing 3 in math, and it doesn't make that much difference. We're looking at the applications and not getting the exact precise value. Rounding errors are going to occur. Now that I have this, let's solve for T1. Let's divide both sides by that 0.5 and say that T1 is equal to 1.638 T2s. Because the 0.5 is being divided by the number, not by the variable. Now that we've solved for T1, let's take that second equation and let's plug in what we know that T1 is. So it starts out with T1, so that's 1.638 T2 times the sine of 60 plus T2 times the sine of 35, which we get, so we'll probably just leave it as sine of 35 right now, is equal to mg, and we know mg is 100. Let's go ahead and satisfy those sines of 60 and sines of 35. So 1.638 times the sine of 60, we're going to get 1.419 T2 plus sine of 35, 0.574 T2. So now we have like terms, and we can add them because they're like terms, is equal to 100. When we add those together, I got 1.993 T2 is equal to 100. And when we divide the 1.993 to the other side, I got 50.176 newtons. I know a lot of people are getting 50 on this one. It really depends on how many decimal places, when are you carrying numbers over, that sort of thing. So we've solved for T2. So now that we've solved for T2 in the second equation, let's go back to the first equation where we said T1 is 1.638 T2s. And let's just take the 1.638 and multiply by what T2 is. 50.176. That helps us solve for T1, and when I solve for T1, I got 82.188. Those boxes are to the right are where we are putting our solutions. It's what they supplied us on the worksheet, so we can summarize our answers on the right side, with T1 being 82.188 newtons and T2 being 50.176 newtons. All right, let's scroll up to number 2. Number 2 out of 3. Same kind of idea, except for this time they tell us what T1 is. They're telling us T1 is 60 newtons, but they're not telling us the mass. So we're going to break that 60 Newton pull that's pulling to the left and up. We're going to see what is the leftward pull, what is the upward pull. The 55-degree angle drops down into the triangle. and we've got 60 cosine 55 going to the left, 60 sine 55 going upwards. To the right, we would have T2 cosine 40, and to the up, T2 sine 40. Since we don't know the mass, we're just going to call it mg, and mg is going to be our force of gravity down. We can start to solve for some of these as we're putting it together. 60 cosine 55 in degree mode from my calculator, I got 34.415. Vertically, 60 sine 55 in my calculator, I got 49.149. On the right side, I'm dropping that 40 into the triangle, T2 cosine of 40, and vertically T2 sine of 40. This will allow me to go ahead and put together that free body diagram where I'm just going to stay constant on this worksheet. I'm just going to show I've got a leftward force, I've got a rightward force. I have 2 upward forces and 1 downward force when I've broken it down to its pieces. When I've got a free body diagram that's a rectangle, that's usually where I'm doing my computations and my analysis of a problem. If I was to create a free body diagram for points, I would just say mg down, 60 newtons up left, and T2 going up and right. Writing it this way also helps me do the net force equations because I can simply see what is left, set it equal to what is right, because it's a constant velocities, balance forces, and the 2 up are equal to the 1 down. So let's go ahead and write the net force equations in this way. I went put the calculation in. 34.415 is equal to T2 cosine 40, and then 49.149 plus T2 sine 40 is equal to mg. Now that top equation is one I can solve for right away. It only has one variable in it, and I will be able to solve for T2. So I'm going to say equals, and then what is the cosine of 40? I think I've got that at 0.766. So I'm just going to divide 0.766 to the other side and solve for T2. And when I did, I got 44.928. And that's my T2. Now I can put that into my second equation and solve for m. I know my second equation, 49.149 plus T2, which is 44.928, sine of 40 is equal to mg. And don't forget, g is 10. Put 44.928 sine of 40 into my calculator, and then I'm going to go ahead and add it to 49.149. When I do that, the value I get is 78.028 is equal to mg, and of course g is 10, so m times 10. So divide both sides by 10, I get 7.803 if we round kilograms as my mass. So mass is 7.803 kilograms. So each question similar but a little bit different, but using the same sets of skills that we're using to understand these problems. Takes us to number 3. We get down to number 3, it looks like we don't know an angle this time. Well, that's going to be fun. So on the left side, T1 is pulling left and up. That total force is 200 newtons. T2 is pulling up and to the right, but we don't know the angle from the horizontal, so we're going to call it theta. It's a generic term for an angle of unknown angle. So we've got 55, drop that down, 200 cosine 55, it's cosine because it's adjacent to the angle, and then 200 sine 55. We can go ahead and calculate these. 200 sine 55 from my calculator, I got 163.83, and 200 cosine 55 in my calculator, I got 114.715. On the opposing side, well, let's go ahead and do down, I guess. Down 20 kilogram mass is 200 down, force of gravity, or weight. T2 cosine theta going to the right, and T2 sine theta going up. If we do our free body diagram, we can show the leftward pull is 200 cosine 55. The rightward pull is T2 cosine theta. Two upward pulls, 200 sine 55 and T2 sine theta. And a simple mg at 200 going down. Forces are balanced. Vertical forces are balanced to each other. Horizontal forces are balanced to each other. We can do our net force equations. 200 cosine 55 is equal to T2 cosine theta. That's the horizontal ones. The vertical, 200 sine 55 plus T2 sine theta, the two upward forces, are balanced to the downward force of mg. Now don't forget they are balanced. That means whatever is pulling to the left is pulling to the right. So if I said 114.715 is pulling to the left, that force pulling to the left, that means the force pulling to the right is also 114.715. Now pulling up on the left side, pulling up is 163.83. Now pulling up on the right side is not also 163.83. It is whatever you have to add to 163.83 to balance it to 200 down. So I've got 200 down minus 163.83 equals what? I got 36.17. So T2 is pulling up with 36.17 because collectively my two ups have to equal my down. So when I add those together, I should get 200. So now to find T2, I'm looking for the hypotenuse of this triangle. And if I'm looking for the hypotenuse and I know the other two sides, geometry taught me Pythagoras. A squared plus B squared equals C squared. If A squared plus B squared equals C squared, which one's A and which one's B makes no matter, but I'm just going to say 114.715 squared plus 36.17 squared is equal to my C squared. So I'm just going to put 114.715 squared plus 36.17 squared into my calculator. I've added them together, hit enter. Now I've got a number. It's a really big number, but don't forget that's C squared, so we need to square root it to then get that hypotenuse, the T2 value. When I did that, I got 120.282 newtons for T2. Finally, we just have to solve for theta. Well, I know three sides of my triangle. T2 I calculated. A squared plus B squared, I feel like that's a little bit less heavy on the calculations. You can use sine, you can use cosine. I'm going to choose to use tangent. It prevents me from having to utilize T2 in my calculations. So I'm going to say the tangent of theta, of that angle, is the opposite over the adjacent. 36.17 over 114.715. So then I can say theta is the inverse tangent of those two divided, and I got tangent, second tan of 36.17 divided by 114.715 equals 17.5 degrees. Put that in the answer box, and that concludes that worksheet.